Hello everyone and welcome to Crustal Deformation and Mountain Building. We are going to concentrate mostly on the crustal deformation aspect of this because we kind of already talked about mountain building when we talked about plate tectonics and when we talked about metamorphism and when we talked about volcanoes and things like that. So we're mostly going to concentrate on crustal deformation. And you can see here in the background I've got our picture of our angular unconformity that we talked about last time from a beach in Portugal. And I looked into this a little bit more and found out that the rocks underneath here, the deformed rocks, are carboniferous in age, which make them roughly 300-ish million years old. The rocks on top here are Triassic in age, which would make them roughly, depending on when in the Triassic, obviously, 200-ish million years old. So you're missing, on the order of 100 million years here between that rock and that rock. And of course, we know that during that 100 million years, this rock got deformed, it got bent, and etc. Just by way of reference, 100 million years ago from now, there were still dinosaurs, and they were nowhere near going extinct. So that's a pretty considerable chunk of time there. But I mentioned that this rock has been bent, and obviously it has. Original horizontality tells us this rock was not deposited this way. Which brings us to, the question of, okay, how do you get rock to bend? Right, because clearly here it has. And our day in, day out experience with rock would seem to indicate that it's really not going to bend. This isn't, you say go bend that rock, people are going to look at you like you're crazy because you kind of are, okay? So how do we get this to happen? Well, okay, we'll get to that, but first let's get some terminology straight because your book is frankly a little bit confusing about this. And so there's some words that we use that we want to make sure we get. So stress. Stress is the force that is applied. And in this case, we're talking about rock. So this is the force being applied to rock, right? Strain is the change of shape as a result of that stress, right? And so I push on the rock or I push on anything and it moves, right? The pushing is the stress. The moving is the strain, right? And if I was in class right now, I'd take a meter stick and lay it on the table with, most of it sticking off of the table. And I would say, okay, look, as I push down on this meter stick, the stress is the force that I apply, right? The strain is the meter stick bending. Now, if I put something other than a meter stick there, let's say I put a really long rock there on the table, right? And now I apply the same amount of stress, I'm going to get a different amount of strain, right? How much strain you get per unit of stress, which would be a Newton or something like that, okay? In fact, it's going to be a Newton because it's a unit of force. But the strain that you get varies from one thing to another, right? If I lay a piece of paper on the end of that table, the force of gravity alone is going to strain it, right? If I lay a meter stick on that table, I'm going to need to apply some more stress to get it to strain, okay? Now, the other word that pops up in your book a lot and is deformation, which is fine. Deformation is the same thing as strain, okay? I have honestly not looked at your book in a little while, but last time I looked at it, they were very, very confused about this. Okay, so stress is the force, strain is the movement or the change in shape as a result of the stress. Did I say that right? Let me say it again. Stress is the force, strain is the change in shape or the movement as a result of the stress, and deformation is the same thing as strain. Okay, so. By the way, if you want to be a geologist when you grow up, and I know a couple of you do, this is structural geology, and you will take an entire class in structural geology, and you will learn all kinds of really cool stuff about deforming rock and then mapping deformed rocks in the field. Okay, so let's take a look at stress a little bit more. So there's a couple different kinds of stress, a few different kinds. One of them is what we would call isometric stress or isometric pressure, right? And this is just, the idea that force on something that is equal in all directions, right? What that's going to do is it's going to change the size of the object, if the object is even compressible, but it does not change the shape of the object, right? And so the easiest way to think about isometric pressure or isometric stress is think about water, right? Because this is something we've all had experience with, okay? Right? You go down in the water and the stress increases, but the pressure slash stress, same thing in this case, increases, but it increases equally on all sides, right? When you go down in the water, you're not getting pressed down, okay, or from the side. You're getting compressed from all directions. If I take a balloon, and you can do this sometime if you like. Take a balloon down to the bottom, a blown up balloon, down to the bottom of a swimming pool and watch what happens, okay? It's just going to get smaller. It's not going to get flatter. It's just going to get smaller, okay? And so, yeah. So that's called isometric pressure. It happens in water. Also happens though if you bury something, right? A little trickier when you bury things. Pressure might not be equal in all directions. There's kind of things that kick in here, but it also fundamentally happens when you bury something. Okay. Now there's also though compression. All right, compression is when I apply stress, in a direction and not in another direction, right? And now this is going to cause a change in shape. Right now, like we can see a block here where I compress it from right and left, and so the block of rock in between, or the block of material in between here, changes shape, right? It gets longer in that up and down dimension where it is unconstrained, right? Where there's nothing pressing up here or down here. So if I press from the side, it gets longer, right? You all know this, right? You know this, right? You all played with Play-Doh, okay? Right? You take a round piece of Play-Doh and you squeeze it between your hands. You make a pancake-looking thing, right? Yeah, compression. Okay, and this is, if we think about this geologically, think about a continent plate boundary, right? Where two pieces of continent come together. So you've got compression on either side, but nothing constraining it vertically, and so you make a mountain range, right? There's also, though, tension, right? And we're going to talk more about this. My slide is weirdly unbalanced, but I'm not going to fix it. Tension, right? Here what we're going to do is, rather than here where we pushed on things, here we're going to pull on things. Now, I don't like these little arrows here with the tension. Pretend they're not there. Because no, that's right. Tension is this arrow and that arrow. Just pulling on something, right? And so that causes what we would call extension, where something gets thinner and it gets wider. You do not need these two arrows here. No, in fact, you don't even want them, because that's something different. Okay, so and if we think about this geologically, we can think about a continental rift. Let's say Eastern Africa. All right, where Africa is breaking apart along that Great Rift Valley, right? And so what's happening there is the Earth's crust is essentially being pulled apart. And finally, today, we're going to get to the different kinds of faults, and we'll see the kind of fault that results from tension, and we'll understand how a geologist can go into the field and see that there's tension without actually witnessing the real-time pulling apart. So Eastern Africa, right? What if we go to California? What kind of stress do we see in California? Well, there we see shear, right? We see, pressure in one direction, in one physical location, and then pressure in another direction, in another physical location, right? And that causes this kind of deformation where one end of your block is going to move one way and another end of your block is going to move another way. Now, in the case of the San Andreas Fault, it actually breaks and slides, but that's not necessarily the case. Right? You can deform rock by bending it. It doesn't always break. Okay, so let's take a look at that. Okay, so that's stress. That's the pressure that we apply, in our case, to the rock. Now, the result of that stress is strain. Okay, now there's two kinds: elastic and inelastic, and rock does both. Okay, elastic strain is where you apply the pressure, the material deforms, okay, as a result of that pressure. That's the strain, okay. Then, though, when you relieve the pressure, the material snaps back, right? And the best way to think about elastic strain is to think about a rubber band, right? If I was standing in front of you, this is where I would pull out a rubber band and I would say, okay, I'm going to pull on that rubber band. There's the stress, right? And as a result of that stress, that rubber band is going to stretch. That's the strain. That's the change in shape, right? But because it is elastic strain, when I let go on one end, it's going to pop back into shape, right? There, okay. So rock will do this. Remember when we talked about earthquakes, right? And we talked about the elastic rebound that is, what the earthquake fundamentally is. Well, that word elastic is used for a reason, because that's what it is, right? That rock is bent to a point, and then when it finally breaks on either side of that fault, it's going to pop back into shape, but it's going to bounce around a little bit as it does, and there's the earthquake. Okay, so elastic strain is very important. Okay, now, inelastic strain is when the material remains deformed. So here, we can do a couple of things. We can break it, or we can bend it. Okay, if we break it, that's called brittle, right? And I think you get that word, right? And so brittle strain is like a fault, right? Where you apply the stress, it changes shape, and then it breaks, right? Now, it's a combination. There's going to be a little bit of elastic strain on either side of that fault as it recovers its shape and bounces back and forth, but the fault itself is brittle, right? That rock broke. Most rock that you deal with on an in and out, day in, day out basis behaves brittly, right? You take it, you smack it with a hammer, and it breaks, right? That's brittle, okay? But under certain circumstances, rock can be ductile. Now, when you think about ductile or ductile, I want you to think, I'm not even sure how you pronounce that, ductile or ductile. Ductile sounds better. If rock is ductile, think about Play-Doh, right? I mean, you can break Play-Doh, but it's actually kind of hard to do, right? I mean, if you push on Play-Doh, it flows, right? And you can deform it all kinds of different ways. That is ductile strain, okay? And so, and rock will do that. Rock will absolutely do that, okay? And so, generally, first step, as we'll see here in a little bit, first step, bury it. Need to bury it, okay? This will not happen at the ground surface. You need to be 10 to 15 kilometers down. That's 6 to 9 miles down at least, maybe even more. I mean, preferably more, actually. At that point, after about 6 to 10 miles, 10 to 15 kilometers down, at that point, the rock is going to go from brittle to at least partially ductile. You're going to have enough heat, enough pressure that it will begin to bend. At least at that point, you have some hope of getting it to bend, right? And not just bending. I mean, there's a lot of different things that can go into rock being deformed, right? It can bend. It can break, it can tilt, it can squash, it can stretch, it can shear. There's all kinds of things it can do here, right? I mean, I chose this picture, which I honestly just found on the internet, because you can see all of that here, right? It's getting tilted. It's, maybe not stretched, but, it's getting, there's a fault right there. So we're definitely getting some shearing and some brittle deformation. You can see all of this bending, which is ductile deformation. It's all been tilted. It's been squashed. It's been all messed up, right? All of this can happen. All of this can happen, right? Now, when we think about deformation, there's a few little things we kind of want to get, right? One is translation, right? Where rock is literally moved, right? And so, if I think about this rock here before it's been deformed, before any pressure has been applied, any stress has been applied, and then I apply it. Well, this chunk of rock right here, it gets moved. It gets literally moved from one place to another, and it is not at all uncommon to be working in the field and come across a sometimes pretty big chunk of rock that really doesn't belong there, and you're like, okay, this has been tectonically moved in, and so you have to take that into account. Things get rotated all the time. You can see some rotation here, you can see some rotation here, you can see here it's been rotated all the way over. This is actually not even upright anymore. It's been tilted all the way over. Rotation's not at all uncommon. And then it can be it can have its shape change too, right? Absolutely. You push on it and the top gets sheared a little bit, gets squeezed. There's absolutely change in shape. And so here's a kind of a diagrammatic view of this, but here's a fold that looks a lot like that. Looks a lot like that. And so now this deformation or strain, same thing, right, produces what we call geologic structures. And there's a few different kinds. First of all, we have joints. A joint is a fracture along with there is no movement. It is a break in the rock along which there is no movement. Okay, on the right here you see some joints, right? You can see them crossing each other. There's a break right there. There's a break right there. There's a break right there. And yeah, those are joints, right? It's just when the rock goes pop and it breaks, but it doesn't move. Okay, this can happen as a result of unloading the rock. Any change in condition can bring about jointing. Now, notice something. Notice here, and it's kind of interesting, the angle between the joints is pretty consistent. This angle is 60 degrees, and this angle here is 120. The rock, when it's very well cemented, it tends to break at 60 and 120 or close just about every time. These are called conjugate joints or conjugate fractures when you get one running this way and one running that way, and that angle between them at 60 and 120. That's very, this angle is not 120 because that's a different joint. This angle is 120, and so but it's very common to get that. Very common to get these conjugate fractures. You can see 60 and 120 there, 60 and 120 there. Yeah, and so really kind of fascinating. You go into the field and you see this a lot. So that's a joint or a set of joints, joint swarm or bunch of joints. Here is some folding, right? And we'll talk more about folding later, characterizing these folds. But let's turn our attention to faults. Because let's turn our attention to faults. So we have two different kinds of fault. We have four different kinds of fault that we're going to put in two different categories. Okay, and the first category are what we call strike-slip faults. Now, this terminology strike, and then later on we're going to get some terminology dip, will make sense by the end. Okay, for now, let's just black box out a little bit and just, okay, strike-slip faults, right? These are faults where the portions of the Earth's crust are moving past each other, right? And so let me bring up a handout and stick it into my PowerPoint. I will be right back. Okay, so I am back. Let's take a look at strike slip faults diagrammatically, and then let's take a look at them in the field. And I'll explain the right lateral, left lateral from the diagram. So you have this diagram in a handout in the module. I will make sure that it is right underneath the this lecture when I get this uploaded, so that it'll be obvious where it is. But these are strike slip faults, right? And what we're doing here is we're looking at these from above. Okay, and there's two kinds, right lateral and left lateral. Let me get back to my laser pointer because it's fancier. And so right lateral and left lateral. And so here's how you tell them apart. Imagine you're standing on one side of the fault and you're looking across the fault, right? And then ask yourself, what direction is the rock moving, right? And so what I've done here is I've drawn the fault with a very thick black line, because that's kind of what we do. And then imagine this is a stream that's been cut by the fault, right? And so there it is, and then it doesn't come out over here. It's been shoved this way, and so it's going to run along the fault, not at all uncommon, and then it comes out here, right? And so if I'm standing here at this bank of the river, and I look across the fault, I have to look to my right to see the river. So it is a right lateral fault. It does not matter what side of the fault I'm standing on, okay? If I stand over here and look across, it's still, from my point of view, standing here and looking across, been moved to the right. Don't, the arrow's going left, but turn it around, right? You're standing here, you're looking this way. Yep, that's been moved to the right, okay? Right lateral, okay? Left lateral is the same, but the opposite. Right now, if I'm standing here, and I look across the stream, or across the fault rather, to see my stream, I have to look to my left, okay? Also, standing here, and I look this way, I still have to look to my left, right? Imagine your little ant standing here on your computer screen, you're looking over here, you have to look to your left to see the stream, to pick up the stream again, right? So right lateral, if you look across the fault and the rock is moved to the right. Left lateral, if you look across it and it's moved to the left. The San Andreas Fault is one great big right lateral strike slip fault. In fact, most of the faults in California, the San Andreas Fault, the Hayward Fault, whatever, choose your favorite fault in California, odds are it's right lateral, right? Because if you think about it, the Pacific Plate is pushing, the Pacific Plate is moving northward, moving, most of coastal California to the north, right? And so if you're standing on the eastern side of the San Andreas Fault, looking toward the Pacific, that block of rock is moving to your right as it gets shoved northward, okay? Both of these are very common at transform boundaries. So if you're in the field and you find a whole bunch of strike slip faults, odds are they'll all be the same kind in the same area. You know that you're on at least what at one time was likely a transform boundary, right? Because that's where you slide this rock past itself. So let's take a look at what they look like in the field, right? Here's a nice one. We can see a coal seam here. There's a rock hammer for scale. We can see a coal seam here coming up to a fault. Now, if I imagine I'm a little ant walking along that coal seam, I need to turn to my right to pick up the coal seam again, right? If I'm a little ant walking this way along the coal seam, I still have to turn to my right to pick up the coal seam again, right? Right lateral, okay? Here's a left lateral, right? Left lateral, here's a body of, I don't even know what that is, rock. It looks like a quartz vein running through it. There's the fault right there. There's a big hammer for scale, big crack hammer. And so we can see that now, if I'm a little ant walking along here, rather than turning to my right to pick up the quartz bed, nope, I got to turn to my left, okay? Left lateral. Okay, if we go out to California and we look here, we can see a classic area here of the San Andreas Fault. And we can see how, this stream, literally a stream, comes flowing down out of these mountains, stops at the fault, and goes off this way, right? And so if I'm standing here and I want to look at the stream, I have to look to my right, right? right lateral. Okay, if I'm standing here and I want to look at the stream, I also have to look to my right, right? I'm turned around. Okay, so right lateral is always right lateral. It just is, right? And so you can see a diagrammatic look at it here. The stream comes running down out of the mountains. This is the North American plate. This is the Pacific plate, right? And so you can see it hits the San Andreas Fault and it's been shoved this way, which if I'm standing here looking across, it's to the right. If I'm standing here looking across, it's to the right, right? And so this is a right lateral fault, right? And honestly, you go to California, you see a lot of this. Okay, you just do, right? Here's a sidewalk, right lateral, right? You look across the fault, been shoved a couple feet to the right. Here's another stream bed, right? Cut by a fault, right lateral, right? And so yeah, now when we talk about strike slip faults, kind of a subcategory of strike slip fault is a transform fault, which is a plate boundary, right? So sometimes people like to use transform faults and strike slip faults kind of interchangeably. You could probably do that, but most commonly a transform fault is a strike slip fault that is also a plate boundary. Right, and so not all. I mean, if we're looking here, this is not a plate boundary, right? Probably, yeah, really not, right? Now, if we're looking here, yeah, right, that's a plate boundary. This one way we set these up, and I talked about this when we talked about plate tectonics, right? Is this area here in between two divergent boundaries, and this is in a way. What the San Andreas Fault is, only it's a bit more complicated than that. But if I've got a divergent boundary over here pushing everything this way, I've got a divergent boundary here pushing everything this way, then this is plate A, this is a plate boundary. We went through all of this in plate tectonics. But you can also see that, right in here, this rock's moving that way, this rock's moving that way. That's going to make lots of those small, shallow focus earthquakes the way we talked about when we talked about earthquakes when we talked about plate tectonics. So people, like I said, people sometimes use transform fault and strike slip fault interchangeably. That's probably okay. I would prefer to reserve transform fault though to a plate boundary, right? So yes, it's a strike slip fault, but it's also a plate boundary, which makes it a transform fault. Now we also have a second kind of fault. And these are dip slip faults. And so with a dip slip fault, we need to look at it from the side, not from above. Okay, and so there's a little bit of terminology we want to get. And if we think about this, so here's a block of rock with a dip slip fault running through it. The block on top here is called the hanging wall, also called the head wall. The block down here is called the foot wall, and it's always called the foot wall. If you imagine a little miner person in here, their feet are on the footwall block, and then where the hanging wall actually comes from is if you want to hang a lantern so you can see, you hang the lantern up here on the hanging wall. I prefer head wall because it makes much more sense. Head wall, foot wall. But okay, we can use hanging wall. Just be aware that some people will use hanging wall, other people will use head wall. Not too big a deal. Okay, I might even go back and forth. So if you hear me say head wall, I mean hanging wall. Okay, so let's go back to this, and we have our strike slip faults here. Now our dip slip faults. We have two kinds, normal and reverse. Okay, so what's happening here is the rock is either being pushed or pulled. And it's either going to get shoved on top of itself, or it's going to get shoved underneath itself, or something like that. Okay, we have two different kinds, normal and reverse. Now, I don't want you to make too much of the word normal here. It's not normal, okay? And I don't want you to make too much of the word reverse here. It's not, nothing's normal and nothing's reverse. It's just what we call them, Okay, this is no more common, this is no less common, etc. So I have descriptions in words here, but I don't know how good those are. Let's take a look. Let's take a look at the diagrammatic view. Now, once again, you have this handout. And I will put a couple of these on the test. Probably one strike slip, maybe one dip slip, and yeah. Okay, so here's what we do. You've got so now we're looking at it from the side. I put a little tree here so that we understand that this is the ground surface. Okay. And then I got a feature running across the fault, right? And in this case, the feature runs across the fault and has been dropped down, right? So in this case, that hanging wall has moved down relative to the footwall, okay? And so, yeah, we call that a normal fault. Normal faults are very common in areas where rock is being pulled, right? Because you can imagine if this is rock and I pull it this way and that way, okay, that's going to cause this top wall, this hanging wall, to slide down, okay? At divergent boundaries, we see a lot of normal faulting. That's how we know those rocks are being pulled on, right? That's how we know that magma isn't forcing its way up in between those two tectonic plates and pushing them apart. It's not. If you go to the Great Rift Valley, where you can see this happening, or go to Iceland where you can see this happening, you're going to see a lot of normal faulting, indicating that this area is under tension, right? It's getting pulled this way, it's getting pulled that way, and oh my gosh, I'm going to try to do something. So let's see if I can draw, right? And so this is so this rock here is being pulled, right? This it's being pulled this way. It's under tension. That's not too bad, although I messed up that, but that's okay. So, like I said, divergent boundaries. This is how we know that magma isn't pushing up in between those two plates, because they're normally faulted. There's just like normal fault after normal fault after normal fault on both sides of those mid-ocean ridges, which once again tells us, I need some water, once again tells us that rock is being pulled. Now, the other hand, the other option here is a reverse fault, right? So I'm going to draw my arrows now because I'm on a roll with arrow drawing. Yeah, right. Okay. So anyway, so here in this case, oh, nope, I'm not drawing. Hold on. There. So in this case, rock is being pushed, right? So now, if I take this rock and I apply pressure like this and I push on it, okay, so what's going to happen now is it's going to break and it's going to slide. Oh, I got better at that just in that one little bit. It's going to break and it's going to slide. And now that hanging wall is going to slide up. Right, if you can imagine, if I have a block of rock and I push on it, it's going to break and this is going to slide up, right? Whereas here, this is sliding down. Okay, and so yeah, so this is called a reverse fault. This is very common at convergent boundaries, right? Where continents or tectonic plates or whatever are coming together. Right, you get a lot of reverse faulting. Right, if you go to somewhere like northern India, Tibet, that northern India, southern China, right? That area, you're going to get a lot of reverse faulting where India is smacking into Eurasia right now, right? Go down to South America, to the west coast of South America, or the Pacific Northwest of North America, right? Where you get these convergent boundaries of one kind or another, you're going to get a lot of reverse faulting because there's a lot of rock getting pushed on. Absolutely getting pushed on, okay? So, now, a little bit of inside geology. Let's say you don't know the fault is there, and let's say that we're going to put an let's say this blue line is economic or a marker bed or something, right? And so we know that when we hit that blue line, we're near I don't know, an oil reservoir, maybe a coal seam. There's something down there that we want. Right, and we know that when we hit that blue line, we're near it. Okay, let's say that we site our drill here. Okay, well, let me go back to drawing because all I need to do now is draw a line, right? So let's say that we sight our, I'm not even going to try to draw a drilling rig, not even going to try. But let's say that we drill here, right? And so we drill and we miss it. All right, we absolutely miss it. If we had drilled over here, we would have hit it deeper. If we had drilled over here, we would have hit it shallower. But if we happen to drill right there, you're not even going to know you're not even going to know it was there. So knowing where the faults are, oh boy, right? You really need to know that. You really need to know that because honestly, this throw can be huge. I mean, it doesn't. It's pretty easy, really, to drill and miss your target. Oops, and absolutely wrong way. Absolutely miss your target because you happen to drill along a normal fault and you didn't know it. On the other hand, here, here, right? If I drill here, I hit it twice. And maybe I need that bottom one, right? And so, man, okay. And this is more common. Maybe you're looking at this as an outcrop and you don't know that that fault is there if you miss that fault. And then you can miss a fault. Yeah, you can miss a fault. It's kind of hard to do, but you could. And so maybe it's a very low angle thrust fault and you did miss it. Now you're going to go, oh, look, there's that blue marker bed. And oh, look, there's the same kind of rock. And you're going to start talking about sequences repeating themselves when it's faulted. So faults are tricky creatures in the field, and you want to be very careful when you're dealing with them. You want to make sure you know they're there, make sure you know what the throw is, make sure you know what's going on because they can make your life very difficult. Let's look at some obvious ones though. So here's a nice normal fault. This is in Mexico, so I can draw on this. I'm gaining drawing confidence. So there's the fault kind of right through there. Okay, so this is on top. So this is the hanging wall. This is the foot wall, right? This rock here is now down here. Okay, and so this hanging wall, I wanted to say head wall. This hanging wall is slid down. Right, when the hanging wall slides down, that's a normal fault. I'm not even going to try to write the word, but that's a normal fault, right? And so what's happening here is when this fault happened, this area was under tension, right? This whole area was being pulled on, okay? And so normal fault. This block is slid down, or you can think of this block as sliding up. Doesn't matter, but yeah, so normal. Okay, here's another normal fault. We saw these already in the Bishop Tough. You can see here. I don't need to draw it. Let me go back to my laser pointer. So yeah, because I kind of made a mess of that. But here's the fault. Right here's a nice bed with a nice light colored layer in it, so we can see it's been slid down. Normal fault. Right now, other side also a normal fault. It's just going in the other direction. Okay, and we see this a lot, right? In areas that are in tension, I'm just going to draw some arrows. In areas that are in tension, where the rock is being pulled this way, there's an arrow, and when the rock is being pulled this way, you'll get these wedges dropped down. Okay, these wedges are called horsts, by the way, Horst. And what it is it's a set of conjugate normal faults, right? In other words, this wedge is the head wall or hanging wall, for both this fault and that fault. Right, and so when you pull that rock apart, what's going to happen is you're going to go chunk, and you're going to drop down one of these wedges, right? And you can see this rock has slid down. This rock has slid down, right? Both of these are normal faults. Once again, this wedge-like structure here is called a horst. It's called a graben. I think I got it wrong before. It's a graben. This is a horst. This is a horst. The down drop structure is a graben. These things can be miles across. You go to an area of the United States in the Southwest called the Basin and Range, and it is just a series of horsts and grabens from when that part of the country was under tension and being pulled apart. And so, not at all uncommon. Both of those are normal faults, right? This wedge, once again, this wedge is the hanging or head wall, sorry. No, I was right. Hanging wall. Yeah, let's just put an H there, why don't we? This wedge is the hanging wall for both this fault and that fault. And in both cases, it slid down, right? And so both of these faults are normal faults, okay? What about a reverse fault? What does that look like? It looks like that. So here we are in China. And rock hammer for scale once again, and once again, here's the, I don't need to draw, you can see, here's the fault, there we go, here's the fault running down through here. And so this bed here has been shoved up over top of this bed. That indicates pressure, right? That's how you get that to slide up, as you push on that rock. You're in China, you expect that, right? At least, especially in southern China. Right, someone puts a gun to your head and says, I'm in southern China standing on a fault. Guess what kind of fault? Guess reverse. Okay, you might be wrong. Things are complicated, but odds are you're right. In this case, this rock has been shoved up relative to this one. This is the hanging wall. This is the foot wall. The hanging wall isn't to the right, or the foot wall isn't to the left, right? The hanging wall is above the fault. The foot wall is below the fault. If the hanging wall has moved up, it's reverse. And you can see a nice bed here of soft sediment deformation, giving us a nice marker bed, showing us that upward motion. I mentioned thrust faults earlier. Thrust faults are very low angle reverse faults, right? And so here's a small thrust fault with only, I don't know, 20 or 30 feet of throw. But this rock here and that rock there are the same. And so you can see that it's a very low angle fault, but this has definitely been shoved up on top of that. The danger in thrust faults is they're so low angle, they can be tricky. This one's not. They can be. They can be regional in scale. This is kind of this is an interesting map, but it's also kind of a hot mess. And all I want you to get out of this is the idea that there's a very large thrust fault along here that is literally miles of throw. And so if you don't know that, you can start talking. Imagine that it's miles from here to here. It's not, but imagine it is. And then you're working up through here. Now remember, these are sedimentary layers, so every layer is an environment or an event, right? And so you're like, first that happened, then you're doing, you're a good geologist, you're doing superposition, you're working your way from the bottom up, you're working out what layers are older, what layers are younger. And then, you're doing environments of deposition as you go, so you can see how things change as you go up. And you're like, first this happened, that happened, that happened, that happened, that happened. Oh, look, and then that happened again, and that happened again, and that happened again, and that happened again, right? Don't do that, right? You missed a fault. Don't miss faults. And people do all the time. So don't feel bad, but you missed a fault. Don't do that. Okay. So, and once again, this one's obvious. This could literally be miles from here to here. Some of these thrust faults, they just go on forever. And if you don't know it, you're going to have a bad time, as they say. So weird map, but cross section showing miles of throw, with that thrust fault. Okay. So, we talked about joints. We talked about faults. I'll put a very simple diagram of one strike slip and one dip slip fault on the test, and so they will be probably just literally cut and pasted from the handout. I will make sure the handout is someplace obvious so that you can have a look at it. And yes. Okay, so joints are pretty simple, at least for us. Faults we talked about. Now let's talk about folds. So folds are where you bend rock. Right, so we saw this before. Here's a nice asymmetric fold. You can see this rock over here is vertical. It wouldn't take much at all to imagine that bending just a little bit more, and it would actually be upside down. In fact, it might actually be upside down here, right? And so, yeah, so how do you get rock to bend, right? How do you get this ductile deformation to happen? Okay, well, there's some things, right? First of all, you need some stress, right? You're going to need pressure, and a lot of it. Okay, you're also going to need differential pressure. Isometric stress, isometric pressure isn't going to do it. Okay, we'll talk about that in 2 more bullet points. Okay, but you are going to need stress. You're going to need, asymmetric stress pushing on the rock, and you're going to need less of it in one direction so that it can bend. Okay, the other thing is take your time. If you push on it too fast, it's going to break. And by time, I mean millions of years. Okay? Take your time. Pressure is helpful too. This does not happen at the ground surface. It's going to need to happen a few miles down, right? And so that's going to provide what we would call confining pressure, okay, to get that rock to bend. Water's good. Wet rock bends more easily than dry rock, so yeah, water's good. And then heat, right? Warm rock is going to bend more easily than cold rock does, which is also one reason to bury it, right? And usually when I give this lecture face to face, I grab a plastic spoon, right? And I spend the entire lecture holding that spoon between my fingers and heating it up and gently pushing on it and gently pushing on it and gently pushing on it until I get it to bend, right? And it usually takes the whole lecture long, and usually at about this point I can hold up a bent plastic spoon. Okay, if I take that spoon and I try to bend it all at once, it just snaps, right? And so I'm applying the stress. I am, relatively speaking, taking time. I'm putting 2 fingers on either side of the spoon to apply confining pressure. In this case, I'm not using any water, but my body heat is providing some heat for it. And if I'm very careful, by this point in the lecture, 45 minutes in, I can have a bent spoon to show you. Okay, that's what it takes. So you do that. Let's go back. You do that and you get it to bend. Okay, now we need a way to describe that bending. Because ultimately what we want to do is we want to go into the field and we want to be able to map these bends in this rock. Okay, this is dipping kind of this way, and this is dipping kind of that way, but it's dipping steeper, and so I want a way to describe this deformation on a map. I need a system. How am I going to describe this deformation on a map? Okay, so we're going to do that using a system that geologists use all the time, and it's called strike and dip. And this is where I really wish that I was standing up in front of you, because I can do this in a way that makes it a bit easier to understand. I considered a lot of different things, but I'm just going to try to do this as well as I can here. So we need to describe the orientation of a plane. Okay, it could be, now in this case, it's a bedding plane. Those are sedimentary layers, and that's that is the boundary between 2 sedimentary rocks. That's a plane, but it could be any plane. It could be a bedding plane. It could be a fault plane. It could be a foliation plane. It could be any plane. Most commonly bedding, and then also foliation, and then also faults. Okay, those are the 3 big ones. Okay, but usually not the ground surface. We have topographic maps for that. Okay, and so how are we going to do this? Well, the first thing we're going to do is we're going to define a line that's called strike. And strike is the intersection of the plane we're interested in. Let's say that it's a bedding plane, okay, because that's the easiest to imagine, I think. So strike is the intersection of that bedding plane with a perfectly horizontal plane. And the easiest way to think about this is maybe think about water. Right, as you know, rising water over our plane, where the water meets the plane, that's the line of strike. Okay, so if I come back, let me see if I can do this here. If I come back here and I look at this, we're kind of looking at this end on, right? And so the line of strike here is kind of moving in and out of the screen, really. If I was to imagine water rising, you know, and imagine this overlying soil peeled off, right? I can imagine that the line where the water met the rock, and that line is actually going to run in and out of the screen. Okay, that is strike, right? If we look here, we can see a line here that is a line of strike. If the rock is tilted in a different direction, the line of strike is going to be in a different direction too. Okay, so there's strike, and I am going to show you in a minute. I'm going to do a quick little video showing you how we take this. But anyway, so there's the line of strike. Okay, now we also have dip. All right, dip is the angle between that perfectly horizontal plane and the plane that you're interested in, right? And so this dip angle here is about 18 degrees. Okay, if I have, you know, once again my plane going like this, and so I've got a dip angle of 18 degrees, and so what I do is I draw on my map, I draw the line of strike as a long line, and then I put a little tick mark in the down slope direction. Okay, and then if I want to, I can put a little 18 beside it, showing that dip angle is 18 degrees. Okay, and so if I look back here at my fold, that dip angle right there is, oh, I don't know, that looks like about 20 degrees, and it's dipping in this direction. This dip angle here, though, is about 90 degrees, and it's dipping in that direction, right? And so if I was looking down on this, and let's pretend I'm looking down on it for a second. If I was looking down on this, my sorry, there we go. So I would put a little strike and dip symbol. Now, once again, it's actually striking in and out of the screen, but there's the line of strike. My dip is this way, and it's about 20 degrees. I can't write with this little thing. Imagine a little. Can I do it? I don't know. Let's find out. 2 and 0. Yeah, I can't write with this. 20. Pretend that's a 0. Okay. And then over here, I would have the same line of strike, kind of in and out of the screen, but now the dip angle is in the opposite direction, right? Too long, but that's okay. And this dip angle here is darn near vertical, right? It's darn near 90 degrees, right? If I think about a perfectly horizontal line here, you know, the angle between the line and the rock is darn near a right angle. If I come over here and I think about a perfectly horizontal surface, the angle here, 20 might be a little generous. That might be a little closer to 15, but you get the idea, right? And so looking down on this structure on a map, the strike and dip symbols would look like this, right? It would be striking, in this case, in and out of the screen, but you get the idea, dipping away and dipping away. Okay, so yeah. So that's how we describe these folds, okay? And let me see. I'm gonna switch to my drawing tablet here in a second, but let's talk about some things, and then I'll switch back to that and show you some other things, and I think that'll work. Okay, so we think about folds. There's a couple of different ways rock can be folded. Right, and so there's a lot of sort of sizes and shapes and geometries and things like that. So we want to get a little bit of terminology. So first of all, the hinge. So let me go back to my pointer. So the hinge is right here, right? It is that point of the maximum curvature of the fold. Okay, so right there is the hinge of the fold. The limb is either side of the fold, right? That's the limb. Okay, if I go back to my example fold that I've been going to over and over again, right? So right here is the hinge of the fold, and I can, there's the hinge of that layer, right about there, right? And so you can see the hinge here, the hinge here, the hinge here, all these different layers, they have that hinge. Now, so that's the hinges of those various folds. And then this rock over here is one limb. This rock over here is another limb. And then there's another thing I can do is I can connect all these hinges. Now this looks like a line on this. Pretend I connected them. Y'all bear with me with this drawing thing. So I can connect all of these hinges to the point where I can make a plane. That's called the axial plane. Okay, now if we really want to get meta, I can take the strike and dip of the axial plane, which in this case would be interesting because this fold has been bent over a bit, right? And so yeah, any plane, right? This axial plane is kind of boring. It's just straight up and down because it's a very symmetrical fold. Right, and so when the rock is bent up like this, that's called an anticline. Okay, and so I like to remember, let me go back to my pointer. I kind of remember it. If I want to make an A, I make a thing that goes like this up, and then I put a little cross across it. So A for make an A, and A for anticline, and the letter A looks like an anticline, right? That's how I remember that. You're stuck with it now. Okay, so if it's been upward, it's an anticline, right? Here we go, right? So you've seen this before without the geologist, but these nice chevron folds, right? And so you can see the hinges here, that point of maximum folding, and then I could also, draw the axial plane if I wanted in here, although in this case the axial plane is kind of curved a bit, so kind of that's the axial plane right there, right? Here's a limb over here, here's a limb over here, and once again, this rock is tilted up, so this is an anticline, right? An A for, looks like an anticline, right? I was stuck with that too. I could put a little, never mind. Okay, so right, here's another one. Right, another anticline. Rock is tilted up. Now notice this doesn't really have anything to do with the ground surface, right? The ground surface here happens to be tilted up. That utterly does not matter, okay? What's going on in the subsurface is it affects the ground surface, but it's also independent of the ground surface. And I'll show you a really good example of that on the next slide. But whenever you see rock bent up like this, that's an anticline, right? And if I was looking down on this on a map and I wanted to draw strike and dip symbols for an anticline, right? The strike is kind of doing like this, and it's dipping. Come on, there we go. Dipping this way, right? And so, for anticlines on a map, they look like this, right? Where, your strike and dip symbols are running this way, and, but then the rock is dipping away. Pretend that's dipping away. I don't know what happened there. Anyway, dipping away, need a longer line of strike, dipping away, right? So this is what anticlines look like. That's my trackpad being funny. Okay, so anticlines. Now, what if the rock is dipped downward, right? Well, okay, so this. So now notice here. Notice that this is a hill, right? The ground surface, let me switch back to my pointer. The ground surface is bowed upward, right? But the rock is bowed downward, right? And so this is what we call a syncline, right? Where the rock is dipped downward. Okay, now, so what about strike and dip symbols? Well, strike and dip symbols for a syncline, right? So here's the direction of strike, same as an anticline, okay? Only now the dip symbols are going this way. I did it again, didn't I? Hold on, can I delete that? I don't know. Let me draw another one. This way, right? Make them bigger. So syncline looks like this. That is weird. It keeps doing that. Okay, hold on. Let me try something real quick. Will this draw on this slide? And not really. Okay, never mind. Okay, let me see. Hold on. Eraser. Okay, so let me get rid of these. Hold on, that's good, and that's good. Okay, so let me go back to my pen. Let's hope that doesn't happen again. So diptych marks are doing this, right? I'm drawing two different sizes, but you get the idea, right? So in a syncline, the rock is dipping toward the center, okay? Whereas with an anticline, as we see back here, the rock is dipping away. Let me now I know how to fix these. Let me fix that real quick and delete that, erase that. There we go. And so I can go back here, and now I can hopefully pull a tick mark there. There we go. And so anticlines look like this, right? With dip directions going away from the axial plane, right? The axial plane is right here, and we can actually signify that with little arrows going out like this. And I'm terrible at drawing these things, but you get the idea, I hope. And so, yeah. So now we're dipping in. Never mind. Now we're dipping away from that axial plane, right? We're over here with the syncline. Here's the axial plane right here. And so now we draw arrows like this to signify that, yeah, this is a syncline. Pretend that's an arrow. This is a syncline, okay? So, boy, I cannot, yeah, drawing with a trackpad is a thing, y'all. It really is. Okay. I'm terrible at it. But anyway, you get, hopefully you get the idea, right? Here we go. Let's look at this. This is fun. Remember this anticline? Right? There's a syncline right there. Right? And this is, and you can imagine, this is not uncommon. This is a very small scale fold. But you can see that, there's an anticline, right? And right beside it is a syncline, right? It's like a piece of paper that's just been wrinkled up into these wave trains. Okay, and so yeah, so in a lot of times, look, right, there's a syncline right here, and then there's an anticline right there, and there's a syncline right there, right? And so, here you have strike and dip symbols doing this. Here you would have them, doing the same thing, but it would make an anticline, and so yeah. So we'll just worry about strike and dip symbols for individual folds, because I know your heads are hurting, because mine hurt when I first learned this stuff too. Most of the folds we've been looking at, I've been drawing, are kind of normal folds like this. Wherein you assume that the hinge doesn't go down into the ground. Okay, if the hinge doesn't plunge, then you just get rock and 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 rock. And so this is an anticline. I'm not going to try to draw the strike and dip symbols, but the dip directions will be out toward the outside of the fold. This is a plunging fold right here. The hinge is going down into the ground, and when you do that, you get this kind of a U-shaped pattern traced onto the ground. Let me get you a picture. Hold on, because I have a really good one in mind. I'll be right back. Okay, so here's what a plunging fold looks like in a diagram. Here's what one looks like in real life. This is just from Google Earth, and you can see, that it noses down, and it makes this kind of a U or C or whatever shape looking thing. This looks like an anticline to me. Rock over here seems to be dipping this way. Rock over here looks like it's dipping that way, and then the axial plane goes down. Okay, most folds plunge. Very rarely does a fold just do this forever. They tend to not do that. Okay, and I kind of know my guess is you have a headache by now. I'm not going to worry too much about plunging anticlines and plunging synclines and the differences between them, because my guess is you'll have a headache by now. And so, so here's, but let's think about this a little bit. I'm going to pull up my drawing board here in just a second. So folds are rarely, if ever, expressed on the ground. In other words, anticlines don't mean the ground is bending up. Synclines don't mean the ground is bending down. Okay, and so you're just walking over some rock, right? And so how are you going to tell the difference between an anticline and a syncline in the field? And then there's another tricky thing that can happen that makes this a little bit more complicated even. And so, but let me switch to my dry erase board, my digital dry erase board, and show you, because there's two ways to do it. There's strike and dip, and there's also the age of the rock. So I'll be right back. I got my drawing tablet up, so let's bear with me because I'm drawing, but you'll get the idea. Okay, um, so let's so let's think about this. So if I'm looking at this from the side, and let's say I've got an anticline, right? And so that means that the rock is dipping like this, right? It's dipping. It's dipping like this. It's dipping like this. I can't draw. Bear with me, please. Dipping like that. Okay, and then we might even have some here that's not even expressed on the ground. Okay, anticline. Right now, I'm not even gonna try to draw this in 3 dimensions because y'all know better than that. But if I look at this on a map once again, right? So if I look at this on a map, and let's just say that this is north, okay, and so the strike and dip symbols would look like this, right? Well, okay. First of all, you would have traces of where these rocks intersect the ground surface, right? And so I would have these traces of rock, and I'm trying to do this kind of matching what I drew down there, but what I drew down there is terrible. So, I've got rock A here, so this is rock A. I've got rock B there, and so this is rock B here, okay? There's that bit in the middle, so that's C. So that's C, right? And then this repeats, right? Because this is A over here again, right? And this is B here again, right? And so this rock and that rock are the same rock, right? So that's still A, and that's still B, right? And then we could call this one D if we wanted to, but we never see it, right? And so assuming the ground is flat, then the ground surface is a horizontal plane intersecting my planes, my bedding planes on my rock, and so the strike symbols all run right along bedding, right? They're all just going to run kind of like this. If the ground isn't flat, we have fancier things we can do, and then the important bit here is that it's all dipping away, right? It's all dipping this way, assuming north is up. Assuming north is up, it's dipping east-west, right? Got that. So this is an anticline, right? A-N-T-I-C. I'm writing on my thing, C-L-I-N-E. I can't write under the best of circumstances. Okay, now what about a syncline? Well, a syncline looks like this, right? So now, looking at it from the side, we have rock doing this, right? We got another rock doing this, and we got another rock doing this. Ooh, that one got really deformed. Okay, so, and then maybe we even have some, like I said, I can't draw. We have some underneath here. I especially can't draw on a computer pad. Anyway, okay, I'm a little better on a dry erase board, but not much. So once again, not even going to try to, do this in 3 dimensions, right? That's not going to happen. Once again, though, as I look at this, I've got a boundary here between 2 different rocks. I got a boundary here, kind of doing the same thing. I've got another boundary here, right? And so, once again, and then all the way over here, I got another boundary over here. And then this is going to be a little bit messed up, right? I got a kind of a boundary there, and then I got one squeezed in here. Ooh, that's not too bad. Squeezed in there like that, right? Okay. So, once again, it's bowed like this, right? And so what I end up saying to myself is, okay, the strike and dip symbols here, once again, the strike is going to be the same as it is for an anticline, right? The strike isn't going to be different, right? The dip direction, though, is, right? Because these are dipping toward the center now, right? So my dip tick marks, which are horrible, are toward the center, right? And and I could put another set of strike and dip symbols over here. I could put another set over here. And these usually happen in lines because what you do is you walk the structure, and you end up filling in your map with the tick marks for the strike and dip symbols, right? So that tells us that the rock over here is bowed upward, the rock over here is bowed downward, right? And this rock and that rock are the same. You don't need me to tell you that again. Okay, so one way to tell these apart is with the strike and dip symbols, right? Which is a perfectly good way to tell these apart, right? You're a geologist, you'll walk a transect across here, and it'll tell you what's going on. Incidentally, if you're a geologist in the field, walk across the line of strike, right? If I'm a geologist in the field and I want to learn about this structure, let me grab the red marker here, and I want to learn about this structure, right? Well, actually, let me grab the blue marker here because I'm going to do the red one for something else. So now I want to learn this structure. I want to walk this way, right? I want to walk across the line of strike, and then I'm going to come over here and I'm going to do it again, right? And look, as I do that, I'm going to see all these different rocks, and I'm going to be able to identify them, tell what they are. I'm going to see, all the dip directions. We're going to see the dip directions shift once again, assuming north is up. The dip directions are going to shift from dipping east to dipping west. Okay, that's good. If you're a geologist in the field, don't walk in this direction, right? You're going to be in the same rock all day long, and you're never going to learn anything, right? If you walk along the line of strike and not across the line of strike, you're going to see the same strike and dip all day long, and you're not going to learn anything, right? You get out of the van here, take that first strike and dip on the first bedding plane you can find, and then let's go back to blue. Blue is good, right? I don't have green. Take that first strike and dip, and then walk, more or less as much as you can, perpendicular to the strike direction. Walk along the dip direction. That's going to get you into all of these different rocks, right? If you're noodling around in here, you can walk all day long, and you're never going to see anything but that rock that's in the middle, and whatever it's doing, you're going to know all about that, but you're not going to know anything about the structure. You're just not. Okay, so that might have been a digression. I don't know. Anyway, okay, so strike and dip symbols will definitely do it for you. Okay, now what else? So, well, the age of the rock. I'm going to try to get rid of all this gunk in here that I just drew. The age of the rock is also a way to tell what's going on, right? Let's say maybe it's all the same rock, that you don't have any changes in bedding, and so it's all the same rock, and so you might not really have strike and dip symbols. This is unlikely, but it'll actually become a little more important here in a minute. Let's think about the age of the rock. Okay, okay, once again, let me finish my labeling here. This is a syncline, right? N-C-L-I-N-E. Okay, now strike and dip symbols going out, or dip symbols going out, dip symbols going in, right? What applied over here for walking it also applies over here, by the way. Okay, let's think about this though. So let's think about some flat-lying rock, right? And let's say that it's sedimentary. Okay, and so superposition applies, right? And so this is rock unit A, this is rock unit B. Let's see, does that work? No, that does not work with my thing over here. Hold on. Let me redo this so that it matches what I've already done, and I already kind of deleted part of that. So let's do that. Okay, so here we go. Okay, so let's say that this is rock unit A. Let's say this is rock unit B, C, D, and E. Okay, now, this is very counterintuitive for a geologist, but that's okay. Superposition tells us that as long as this is sedimentary rock, and as long as it's flat-lying, hasn't been flipped over or anything, that this rock down here is the older, this rock up here, UNG, is the younger. Okay, so A is the youngest, E is the oldest. Okay, now if I take that and I apply pressure to it, right, and let's say I make an anticline, right, so I bow all the rock upward, right, so let's physically do that. Let's bow this rock upward. Let's see, I'm really stretching my drawing skills here, but that's okay. And so I bow this rock upward. Okay, now, and so okay, so I just made an anticline. Now let's erode it, right? Let's erode it flat. So I'm gonna erase. Let's see if I can actually get this to work. I don't think I can. Let's erase this here. I can't, but that's okay. You'll get the idea. So now this is the ground surface, right? And so now this is rock A here. I think I didn't. I think this is A. I'm not sure. The youngest rock here, right? This is A here. This is B here, right? Notice that B is older than A, right? So what anticlines do, and I did a really bad job of drawing it, but what anticlines do is they push the older rock up in the middle. Right, and so in an anticline, what you're going to have is you're going to have the older rock in the middle, and you're going to have the younger rock on the outside. In a syncline, they push the older rock up to the surface on the outside, right? So anticlines, you have the older rock in the middle because that deeper rock has been pushed up, and the younger rock on the outside, right? So if I walk from here to here, I should walk progressively from older rock into younger rock. Out here, the younger rock is in the middle, and the older rock is on the outside. Okay, so there's two ways to tell if you're in an anticline or a syncline. In an anticline, the older rock will be in the middle because the older rock from deeper has been pushed up. I did a really bad job of drawing that over there. Sorry about that. The older rock's in the middle, been pushed up. The younger rock is on the outside. Okay, in a syncline, it's just the opposite. The older rock's on the outside, and the younger rock's in the middle. Okay, let me show you one kind of special case of something where this older and younger is gonna make a difference. Okay, and I'm actually gonna actually let me do it this way. Hold on, let me just clear this whole mess and start again real quickly here. And so, where's my clear this whole dang thing? Export clear canvas. There it is. Okay, there we go. So let's think about this. Okay, so let's draw an anticline, right? And so once again, rock is kind of doing this. And rock is kind of doing this on the other side. This is an asymmetric anticline because I can't draw, but you get the idea. And so let me draw it. Let me go ahead and bring it out of the frame. There's our anticline. That's a terrible anticline, but you get the idea, right? And so, as we just said, the older rock that would normally be deep gets pushed up. You have younger rock on the outside, younger rock on the outside. Okay, now, let's apply a lot of tectonic force to this. And let's take this whole thing. Now, this is entirely possible. It happens. I promise you this happens. Let's take this entire thing and flip it over. Right? If I take this structure and I flip it over, now it's going to do this. Right? Suddenly, the strike and dip symbols are going to tell you, right? So what I've done is I take this whole thing and flip it over, right? Literally turn it upside down, okay? Now, the strike and dip symbols are going to look like, on a map, are going to look like this, right? It's dipping toward the center, right? But hold on, right? Because it's that you go, well, it's a syncline. You're okay. Well, get on with your life. No, it's not, right? No, it's actually a synformal anticline, and I know I might have just made your heads explode, but that's what it's called, a synformal anticline. Okay, because it's an anticline that's been flipped over. Okay, how are you going to tell? Older rock still in the middle, younger rock still on the outside. Same thing for an antiformal syncline. If I take a syncline, I flip it over, the younger rock will be in the middle, the older rock will be on the outside. It's not common, but it happens. And so if you're in a very isolated area you're like, okay, I'm mapping a syncline, check the age of the rock. Make sure that if you think you're mapping a syncline, that younger rock is in the middle and the older rock is on the outside. Because right, if you take an anticline and you flip it over, right, this older rock down here, let's call it rock 1, that is older, right, it's underneath. Now that becomes that older rock right there, and yeah, okay, so that's also rock 1, which is also older. This is not a syncline. This is a synformal anticline. That may be too much inside baseball. I don't know. But anyway, all this happens. You go somewhere like the Appalachians where things are just all messed up. This absolutely, positively happens. Okay, I'm going to go back to my PowerPoint. I will be right back. Okay, we're back. And so once again, 2 ways to tell an anticline from a syncline. The first is strike and dip. Right? In an anticline, the dip direction is away from the center of the fold. In a syncline, the dip direction is toward the center of the fold. But folds get flipped over. But in an anticline, the older rock will always be in the middle, right? Because that middle rock gets pushed up. In a syncline, the older rock is on the outside, right? These are not often expressed at the ground surface, right? The ground surface is what the ground surface is. So here we can see that we have rock here that is older. Superposition tells us that. It's further down. And here it's exposed on the ground surface, right? Rock over here is younger. Superposition tells us that. And here it is exposed on the ground surface. Older rocks in the middle. Younger rocks on the outside, right? Syncline, just the opposite. You're going to push this up. And so now you're going to have the older rock on the outside. This rock that's deeper and should be deep, well, is deeper, is going to be older on the outside, younger in the middle. And then here's the picture I wanted to actually show you of some plunging anticlines, plunging synclines. This is what they look like. You get these V or U-shaped traces on the ground. In addition to anticlines and synclines, there's a couple other quick things to pick up. Monocline is just kind of what it sounds like. One fold. These are kind of very common when you have blind faults that don't breach the ground surface, and so you'll get rock, with one limb. Right, this isn't dipping over here and over. No, it's just dipping right there. Right. Once again, that's called a monocline, and a lot of times they happen where you have blind faults. Here's one here. Right, this is a monocline. Right, one you can see it's been cut by a river, but you can see, there's not a, another fold dipping the other direction over here. There's not another fold dipping this direction. No. Just that one dip slope right there. We also have domes and basins. Where here, you just push the rock up almost in a circle. These are very common over salt deposits where rock gets pushed up. They can also be very common on top of bodies of igneous rock where rock is getting pushed up. So a dome is like a bowl turned upside down. A basin is kind of like a bowl turned right side up, right? And so same thing with anticlines and synclines though, right? You're going to have older rock in the middle, younger rock on the outside. Here you're going to have older rock on the outside, younger rock in the middle. So yeah, here's what they look like, but here's what a nice dome looks like. From the air. So yeah, not quite so common. You don't do this a lot, but you do it a little bit. What's way more common though are plunging folds, plunging anticlines, and plunging synclines. Okay, I'm going to do another video in the field because I want to get into the field. I feel like I need to do that on how we actually tell strike and dip in the field. And I'll probably go do that. I don't know when, but I'll do it before the end of the semester. It's totally optional. It's totally inside baseball. But if you want to be a geologist when you grow up, I'll show you how we measure strike and dip in the field. Okay. But I'm going to go ahead and get this up and get it loaded, and we'll be good to go. Okay. Talk with you all later on. Get me if you need me, as always. Okay. Bye-bye.